Hi, everybody. Welcome back to Dave's Math channel. This is my second video in my series on algebraic number theory. Today I'm going to talk about what's probably the most basic concept in algebraic number theory, namely number fields. And I'll get to this diagram later, but let's just begin. So first, before we start talking about algebraic number fields, we have to talk about what a field is. So a field is a more basic concept. Field is just a set with two binary operators, named what we usually call them addition and multiplication, satisfying the following five axioms or properties. And there's properties associated with addition as well as multiplication. So the first one is associativity. You probably learned these all when you learned about real numbers. Real numbers are an example of a field. And so rational numbers, it turns out, but integers are not. Integers are what are called a ring, but I'm not going to talk about rings today. I might talk about them in a future video because they're very important as well. But for now, we're just talking about fields. So fields are associative both with respect to addition and multiplication. A plus B, it doesn't matter how we group terms, either when we're adding or when we're multiplying. And they're also both commutative, so the order doesn't matter for addition or multiplication. And they're also distributive. And I guess there's two distributive laws. They're not strictly with respect to addition or multiplication, it's just two different laws. So just like we learn in grade school, A times quantity B plus C is A B plus AC, or the other one is A quantity plus B times C is AC plus BC. Those are the distributive laws. And then there's the additive identity element, zero. So we call the added we always give the name zero to the additive identity element of every field. It has to exist. So it's not a field unless it has an additive identity element, which we call zero. That's just a number such that if you add that to any other number of the field, you get back the other number. So a plus zero is 0 plus a. They're both equal to a. And similarly for multiplication, there's a multiplicative identity element, which we call 1. So 8 times 1 is 1 times a, or a. So we always have these two elements, 0 and 1. Finally, we have additive and multiplicative inverses. But you have to be a little careful with multiplicative inverses. So additive inverses of every element of a field always exist. So for every element A of a field, there's another number which we write as minus A. You can think of it as the negative of A. Just that A plus the quantity minus A is 0, and that's also equal to minus A plus A. So then similarly for multiplication, you have the same idea, except we call the multiplicative inverse a to the power minus 1. Sometimes you say that's the inverse of a. So a times its inverse is equal to 1, and so is a inverse times a. But you have to be careful here because 0 does not have an inverse. You can't divide by 0 in a field. That's the only thing you can't do. Fields are closed with respect to every operation involving addition and multiplication, except you never divide by 0. Just like you can't for real numbers or for rational numbers. Like I said, those are examples of fields. So that's what a field is. Pretty simple. And then a number field is just a special type of field. It's a field of algebraic numbers. So the elements of a number field are algebraic numbers. I defined algebraic numbers in the previous video I made, the introductory video. And the addition and multiplication is ordinary addition and multiplication of real or complex numbers, as the case may be. Some number fields are subfields of the field of real numbers. Some other number fields are subfields of the field of complex numbers. And these are usually known as real number fields or either imaginary or complex number fields. And there's examples of both. And here's 5 examples. So the simplest example of a number field is just the field of rational numbers. It's not. It's a small. Another way to think of the field of rational numbers It's the smallest possible number field. It's the smallest possible field containing only rational numbers except for the trivial field. It turns out that, actually, that's not even true because the trivial field would just contain the element 0. I don't think that contains 1. So maybe that's wrong. I don't think the field containing the element just 0 is a field. So forget what I said. That the field of rational numbers is the smallest possible um, algebraic number field. They're just number field. Sometimes we call them algebraic number fields. Sometimes we just call them number fields. So that's an example of a number field. And then a little bit more interesting examples. We have the algebraic numbers of the form a plus b times the square root of 2, where a and b are now arbitrary rational numbers. So for instance, 1 plus square root of 2, 3 minus square root of 2, 4/3 plus 5/7 times the square root of 2. Those are all elements of this number field. And that is a number field. You can prove it's a number field. I'm not doing it here. But these are all number fields. All these examples I'm giving you are examples of number fields. And there's kind of shorthand notation for this field of that I just described in an example 2. We can write it as q plus 2q times the square root of 2, where you just imagine you can substitute arbitrary rational numbers for each of the q's. And they don't have to be the same, but they can each be arbitrary rational numbers. Those are all the elements of this field. And a more simpler way to write it is we just write q, and then we write square root of 2 in parentheses next to it. Sometimes we call this q adjoin square root of 2, or just q of square root of 2. So that's another example of a number field. Similarly, you can do the same kind of thing, except you can replace square root of 2 by I. And remember, I is a square root of minus 1. It's just another square root. And this is a subfield of the complex numbers. It's not a subfield of the real numbers because I is not a real number, as you guys all know. It's the imaginary unit, which is not real. So we have numbers of this form, a plus bi, where once again, a and b are arbitrary rational numbers. And just like before, we can write this as q plus qi, or we can just simply write as q adjoint I. So that's another kind of similar example. And then example 4, we have numbers of the form a plus b times the cube root of 2 plus c times the cube root of 4. It turns out if you just did a plus b times the cube root of 2, that is not a number field, it turns out. Because you're going to get the cube root of 4 in that field, but that wouldn't be a number of the form I wrote down. So you need both the cube root of 2 and the cube root of 4. And this is also a field if you join. So we can write this as q plus q times the cube root of 2 plus q times the cube root of 4. And it turns out this is also equal to q adjoin cube root of 2. You don't have to join the cube root of 4 as well. You kind of get that one for free. And then you also have this set of algebraic numbers of the form a plus b times square root of 2 plus I times c plus d times square root of 2. So this is a complex field. This is a field of complex algebraic numbers. And we could write it as q plus q times square root of 2 plus q times I plus q times I times the square root of 2. But it turns out that it has just two generators. These things inside the parentheses are called generators. I'll get to those next. But you can write this fifth example, this last example, is q adjoin square root of 2 and I. So these are all examples of number fields. And a nice thing about number fields, there's also a thing called number field extensions. So the nice thing about putting these things in parentheses, these things are called generators, the things I'm putting parentheses. So we have this kind of hierarchy of number fields. So you got q on the bottom. Q is the smallest possible number field. But then you have these three extensions of q. You have q of square root of 3, q of square root of 6, and q of square root of 2. Those are all, they're called quadratic extensions, by the way. I haven't gotten this in this lecture, but it turns out that every field extension has what's called a degree. over its subfield. So quadratic number fields are just number fields of degree 2. So all the fields on the in the middle are fields of degree 2 or quadratic number fields. And then above all that, you have q join square root of 2 and square root of 3. It turns out you get square root of 6 for free because square root of 6 is just square root of 2 times the square root of 3. So the thing on top is what's called a biquadratic number field. It has degree 4 over q, but it also has degree 2 over q joint square root of 3, q joint square root of 6, and q joint square root of 2. So, always have this kind of structure with number fields. And, this is important. I mean, this comes in play a lot when you study Galois theory. I'm not getting into Galois theory in this particular lecture. I'll probably do that in a future one. But anyway, um, so that's what number field extensions are, and then I mentioned generators already. So it turns out that every number field, which I'm calling K here, has a what's called a generating set. It's just a set of algebraic numbers, which I'm writing as alpha 1, alpha 2, up to alpha n. So it has n generators. And what that means is that it's the smallest possible, it's the smallest extension of Q, or the smallest number field, if you like, that contains each of these elements. Um, so each of these elements is a generator of the number field. And you get a lot of other stuff in there for free. For instance, you get all products of elements of the generating set, like alpha 1, alpha 2, that's in there, alpha 1, alpha 3, in general, alpha I, alpha J, or you don't have to just multiply 2. You can multiply 3 or more. You can add elements. You can do a lot of stuff with them because it's a field. And anyway, that's a generating set, and the elements of a generating set are called generators of the number field. So let me just give you some examples. These are really the same examples I went over before. So the first non-trivial example that I gave you before was the field of algebraic numbers that form a plus b times the square root of 2, where a and b are rational numbers. And we can write that as q joint square root of 2, like I said. And the reason we write it that way is because the square root of 2 generates this number field. And similarly, the number field of algebraic numbers that form a plus bi, where once again a and b are rational, that we can write as q join I. So I is the generator of this number field. And then the third example, if we have algebraic numbers that form a plus b times square root of 2, or cube root of 2, plus c times cube root of 4, then that actually has just one generator, cube root of 2. Because like I said before, you get the cube root of 4 for free just by squaring cube root of 2. So we can write this field as q adjoined cube root of 2. So it has a single generator, cube root of 2. And finally, the last example here, the field of algebraic numbers of the form a plus b times square root of 2 plus I times c plus d times square root of 2, where once again a, b, c, and d are all rational. This one has just two generators, namely the square root of 2 and I. So we can write k as q adjoint square root of 2 and I. You get I times the square root of 2 for free. So anyway, those are just some simple examples. And then there's an important result in algebraic number theory known as the primitive element theorem. This is a very difficult theorem to prove. And I don't even remember the proof myself. I learned it when I was in graduate school, but I've forgotten it since. It's a very difficult theorem. I think it was proven fairly recently, I think in the 20th century. But what the primitive element theorem says is that every number field, every field extension of Q, in other words, every number field, every algebraic number field, it has a primitive element. It has what you can write it in terms. You can give it just one generator. You don't need more than one. It turns out that every algebraic number field can be generated by a single algebraic number, which we call a primitive element of the number field. And it's not necessarily unique. As a matter of fact, most of the time it's not. But there does always exist a primitive element. And I'll just give some examples below. It turns out that the field K equal to Q adjoint square root of 2 and square root of 3. We can actually write this as Q of square root of 2 plus square root of 3. So it turns out that the square root of 2 plus the square root of 3 is a generator of this field. It's not very easy to prove, but you can prove that you can get the square root of 2 and the square root of 3 and the square root of 6 out of this field. You can get them just from square root of 2 plus square root of 3. And then another example that's sort of like that is, here we have a degree 8 field. This is a pretty big field. Q adjoins square root of 2, square root of 3, and square root of 5. So here we've written it with 3 generators that are all square roots, but it turns out it has a primitive element, square root of 2 plus square root of 3 plus square root of 5. And this is even harder to prove, but you can prove that you get all these things, square root of 2, square root of 3, and square root of 5 out of this field. And of course, you get a lot of other square roots too, like square root of 6, square root of 10, square root of 15, and square root of 30, I think. And then the third example, I think I already gave this example, the, the field generated by square root of 2 and I. It turns out that a primitive element of this number field is I times the square root of 2. It's actually not too hard to prove this. Or you can write this as a square root of minus 2. It's usually, by the way, usually we write I times square root of n, where n is a positive integer, as we write that as square root of minus n. It's just easier. And so we write this as q adjoins square root of minus 2. So square root of minus 2, or if you like I times the square root of 2, is a generator of this number field. And then finally, here, this one's probably the most complicated example I'm going to give today, but we have this number we call omega. This is what's known as a primitive cube root of unity, and it turns out that omega is equal to 1 plus I times the square root of 3 over 2. If you like, it's a complex number with an argument of 120 degrees, or 2 pi over 3 radians. It's a complex number on the unit circle that's 120 degrees counterclockwise from 1, which points to the right. So this point's kind of northwest, or if you like, kind of north by northwest. 120-degree angles. So anyway, that's what we call omega, and then the example I'm giving here is um, the number field, q adjoin cube root of 2 and omega. And it turns out that this one has a primitive element. You can just multiply omega times the cube root of 2. So this has the primitive element, omega times cube root of 2. It turns out this field has degree 6 over the real numbers. So pretty complicated number field. But anyway, those are the examples. And that concludes my video for tonight. My introduction to algebraic number fields, or number fields, which are kind of the most basic concept in algebraic number theory. We use them a lot. I've just defined them in this video. I think this lecture series will get more fun the more we do, because we'll start solving problems involving these things. And, I think it's pretty cool. But anyway, that completes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time.